Let's see what the good doctor is saying.
Is a coincidence. And this is very interesting. It has been noted by a couple of heterodox scientists, interestingly. And I mean, two things to mention here. Why did I insert this p over 2? Because
Okay, pi over 2. That's essentially what he's saying there, because you could pronounce pi, p, whatever. I understand what he's saying. So basically the claim is, this is all we really need here, is the approximate value of Planck's constant is about equal to pi divided by 2 times c, the speed of light, times the mass of the proton, times the radius of the proton. Cool. All right, so we don't need that. So let's actually go to it to where I actually have some tabs set up for this. So let's get nerdy, everybody. All right, so now we can do the window. All right, here we go. Okay, so Dr. Unzicker is saying, he's pointing out, and again, other folks have pointed this out, that if you take this following expression, basically pi divided by 2 times c, the speed of light, times the proton mass, times times the proton radius. Now, note, this is something that Wolfram Alpha helped me, because, see, we have an option up here. It says, assuming the proton mean square charge radius. Okay, that's generally what we refer to as the radius of the proton. And there was a big thing where we thought it was about like 8.7 or so femtometers, or 10 to the minus 16, whatever magnitude that comes out to be. And apparently some more recent measurements seem to disagree with that long-held thing, and we had some confirmation, and ultimately it looked like the proton radius was a bit smaller, by about like 3 or 4%. That doesn't sound like much, but if you're talking it's like 16 significant, it ends up being pretty big difference. Okay, so as we can see here, when we put that all in, we get about Planck's constant, h. Okay, so we get the first couple of digits over there. All right, that's really cool. And again, it's pretty close to Planck's reduced constant. It's about 2 pi off, because that's the difference between Planck's constant and Planck's reduced constant. Cool. All right. So let's see, where do we go from here? Okay. So seeing that, I'm like, of course I had to go down a Wolfram hole. So what do? First off, one of the things I learned from that, let's just look at the dimensional components. So let's just take off that dimensionless pi divided by 2, because that's a modifying term. Okay. So again, in Wolfram Alpha, we need to clarify. It's saying, oh, C, the charm quark? No, we want to use C as in the speed of light, a unit. Okay. And we're doing multiplication. So we do this. It's like, all right, that's pretty cool there. So one of the things that I noticed is it gives us an option here, assuming the proton root mean square charge radius, whatever that is. Wait a second, there's an option. We can use the classical radius instead. So basically that's just assuming spherical things there and everything. So what happens if we click this? Okay. So let's go through. So we've got our same thing, except we took off that pi divided by 2 dimensionless modification term, and we have c, the speed of light in a vacuum, times the proton mass, times the proton's classical radius. Okay. What does it give us? Gives us these numbers. Those numbers don't mean a thing to me. Now, what caught my eye is, wait a second, it's about 137th the value of the reduced Planck's constant. For those of you that have been catching up with some physics and or pop sci, you may have heard that whole 1 over 137. Like even in, was it Rick and Morty? Rick Sanchez, the primary one, is from universe 137. Ah, see, pop sci references and everything there. So that got my noggin a jogging, because it's about 1 over the fine structure constant. So of course, we had to play. So we go over here. So we take that whole thing. We're taking the speed of light, the mass of the proton, and then we're taking the proton's classical radius, and we're just dividing this whole thing by the fine structure constant. And then we get these numbers here, which, oh, looky. This seems to be about the first 9 significant digits. Planck's constant is defined at 10, so the last digit here should be 17, but the speed of light only has 9 digits going in. So it seems to be rounding up, so it seems to have about 1,000,000 times more agreement if we rephrase it in the form of Planck's reduced constant, hbar, rather than Planck's constant. I think that's pretty neat. But wait, there's more. So of course, if this happened to work for the proton, that raises the very next question. Is this just a coincidence? Or might it be trying to tell us something? Might there be something interesting going on here? So, we did the calculation for the electron. So again, we're doing the same thing here. We're taking the mass of the electron times the electron's classical radius times the speed of light divided by alpha, the fine structure constant. Looky, these numbers look very similar. Oh, this, again, seems to be the same numbers. Huh, that is... I was not expecting this at all! So it does seem to hold there. And, oh yes, welcome, Rick. One of my teachers here is in the chat. It's good to see you. I hope you are recovering, my friend. I look forward to seeing you in the future and having more discussions, because I've learned a lot. You are definitely, between you and Stephen Wolfram, you're basically the folks that helped give me the actual gumption to actually come out and become a monk at the physics monastery. So thank you. This literally wouldn't be possible without a extremely low probabilistic series of events. So I thought this was pretty cool. So let's continue. Okay, so if this simple expression, I claim, happens to hold for the proton and the electron, well, that leads to the next question. What happens if we do it for the neutron? So I tried, and let's do this. We'll duplicate this tab, and then let's just replace a couple of things. There's a little bit of a twist here, because if we try to do this for the neutron, so the neutron mass, which we do have, it's a little bit more massive than the proton, and then let's try the neutron. I don't think it really has a class. Long story short is we don't have enough data. I believe right now we have the neutron to about neutron's radius to about 0 significant digits. We might have its Compton wavelength, but ultimately we don't have enough. So I'm like, oh, what can we do? So what I did was I applied the awesomeness of algebra. What the heck am I talking about? What am I talking about is, well, if we claim that this should hold for the neutron as well, all we did is, we know the neutron mass about 10, 12 significant digits-ish. Well, if we assume this hold and it should equal hbar, well, we can solve for x. So I literally just put in x meters. Oh God, I can't even spell the neutron right. Wow, it's a good thing Wolfram Alpha carries me. Okay, so we get this number for the classical radius of the neutron. Okay, so we took that and we just plug it back into our expression. So we're taking the speed of light times the mass of the neutron times this estimated classical radius of the neutron divided by the fine structure constant. Oh, and lucky. Of course we're going to get the same thing because we literally set it equal to that. Now, this classical radius is interesting because, number one, it's a little bit smaller than the proton's classical radius. And you're like, wait. The neutron is heavier. Shouldn't it be bigger? Some people speculate that it is, but if we're going to take what we've learned from some astronomers and cosmologists, it's like, well, once you start getting to a neutron star, the more mass you add, the smaller it gets. that does seem to hold up here. So, hey, Jedi. Good to see you, my friend. Good to see you. Listen, I'm just providing a little bit of something that I found. And full disclosure, we need to give credit where credit is due. Upon doing some of these calculations for, especially, I think it was the radius of the proton, because that's the interesting thing, because there's a way to go back and forth between this. Did I have this next? Okay. So which one was this? Okay, so this is when you divide by 1/4 alpha for the proton and neutron, it does seem to give you the RMS, or the root mean square radius there. Okay. So this is for the neutron, which is interesting because it's a wee bit smaller than the proton radius that we can calculate, which, let's see, where is this? I gotta go through it. Okay. So this is basically applying the same thing. So this is the mass of the proton in kilograms. This is the speed of light in meters per second. And then we're solving for x, because hbar is the elementary unit of action. Its dimensions are mass times an area divided by time. So we got mass, we have length squared, which will literally give us an area, and then divided by a time, which will give us a mass area rate, aka the units of action. Okay, so when we do that, we get this number out here, that 8.4123, yada, yada, yada. So coincidentally, if we go to, what was it? Hold on, I got, let's bring up code data, proton radius. All right. So as we can see, the proton RMS charge radius, so the root mean square. This used to be about 8.7 or so. The more recent measurements seem to put it at about 8.40, and then we got pretty big error up here. So that means these last two digits, we could either add that 64 to bring that up to a 1 and something, or subtract it. So that would go down to about a 40 or so. So at least we're in the error bars there.